Welcome to the second video of the powder sample introduction system for ICP-OES. Today we'll look at the first analysis results. My name is Marius and thank you to Joban for giving us the instrument to work with. A little bit of an overview. We'll look at the analysis protocol, the sample description, sample introduction and replicate measurements, as well as the instrument parameters and integration parameters. Remember that there's no calibration, so no concentration results, only intensity values. And then we'll also look at the analytical emission lines. Bit of a review. Previously we understood that the sample introduction was a little bit erratic. We'll also look at the investigation to the internal standard lines. It was a glass matrix, so we'll look at the silicon as an internal standard. The instrument parameters, the plasma, as well as the integration parameters, and then the selection of silicon emission lines. The initial selection, iteration of analyte to internal standard line ratios, as well as the final selection. Then we'll look at the spectra for the analyte lines, as well as a few silicon lines. The precision, and this is probably the crux of the whole story, is the precision with and without an internal standard and what the improvement was. Conclusion and some future work doing a complete calibration, set of samples, CRMs, and re-evaluation of the internal standard lines. So if we start off with the sample, it was an amber glass a container glass. It was an imported beer bottle. This sample was ground in a tungsten carbide mill, so the sample will contain some tungsten. The typical composition of an amber container glass is 72.5% silica, some soda and calcium. There will also be some minor components, which include magnesia, alumina, and potassium. The coloring components are chromium trioxide as well as aluminium trioxide. Iron trioxide, and then also some sulfur to act as a reducing agent. There are some trace elements, including titanium, manganese, copper, strontium, barium, and a little bit of lead, as well as some ppm to ppb levels of other elements. The ICP Analyzer Pro software from Spectra allows us to capture and store the complete spectrum with each and every analysis. This means that later on we can add or remove emission lines. We can add, remove, or change peak and background positions. And we can also choose the integration parameter for each and every emission line. Lastly, we can add, change, or remove internal standard lines for each analyte line. The sample introduction system was the powder sample introduction that we saw previously. I did 3 replicate measurements, and for each replicate measurement there were 5 integrations. That means that there's a total of 15 spectra for each sample, for each analyte. More information a bit later on. So the ICP torch and orientation, it was set up in the radial observation mode. The torch has an additional gas inlet, which adds argon tangentially to the injector tube. So on the left hand side we can see the there you go, the nebulizer gas inlet in there. Some additional gas comes in tangentially, and then the typical auxiliary and coolant gas. The instrument was set up to run at 1400 watts with a coolant flow of 13 liters per minute, auxiliary 1 liter per minute. Then the nebulizer was set at 0.85 and additional gas at 0.3 liters per minute. The back pressure on the powder sample introduction was high, around 400 kPa or 60 psi. and that the ICP could not regulate the nebulizer flow rate above 1 liters per minute. For that reason, I chose to keep the nebulizer flow rate at 0.85 liters per minute and add additional gas afterwards. So the instrument that I used contains CMOS detectors, and CCD and CMOS detectors have excellent quantum efficiency. Almost every photon that falls onto the detector is converted into a signal. However, CCD and CMOS detectors have very short linear response ranges, only 1 or 2 orders of linear response range. The integration interval times must be adjusted to cover the specific intensity range, similar to a camera shutter speed setting. This way we can cover 9 orders of magnitude, from tens of counts per second up to tens of billions of counts per second. So this shows us the integration time for each integration, as well as the interval time. So we started off with 0.1 milliseconds, then 0.1 milliseconds, 1 milliseconds, 10, 100, and 1,000 milliseconds. That would give us maximum intensities of 1.2 billion counts, 120 million counts, 12 million counts, 1.2 million, and 120,000 counts for each of those integration periods. So remember that there was no calibration and thus no concentration results. However, the concentration is always a constant multiplied by the intensity. Thus the precision for the concentration will be the exact same as that of the intensity. We started off with analytical emission lines, and I chose several primary emission lines for each analyte, typically 3, maybe 4. This helps to confirm the presence or maybe the absence of elements. Unfortunately, there's only one useful lithium emission line. I used the instrument software database as well as the NIST atomic spectra database as a backup or a reference. So previously we saw that the aspiration was erratic. It caused varying intensities which we could observe visually, and then that translated into poor precision. We need to find a way to present a sample that causes less clumping. We know that internal standards help improve precision. The analyte and the internal standard are measured at the exact same time. So whatever influences the analyte will also influence the internal standard, and the precision of the ratio of analyte divided by internal standard will be much better than the precision of the analyte alone. So we started off with looking at the internal standard lines. The sample was a glass sample, which obviously is a silicon matrix, and we used silicon as the internal standard. I started off with initial selection of emission lines, silicon emission lines, and then did an iteration of analyte to internal standard lines, and then made a final selection. I selected 97 of the known silicon emission lines, and I tried to have a range of intensities. Remember the 5 integration systems that I had. Highest 1.2 billion counts, 120 million, 12 million, 1.2 million, and 120,000 counts. Try to use both atomic and ionic lines. Silicon unfortunately emits mainly from the atomic state, and only a few useful ionic lines were available. Each analyte line was ratioed against each silicon emission line. A matrix was generated with precision results, and I selected the pair of lines with the lowest percentage RSD, and I calculated the improvement factor for each of those. So look at the spectra on the right hand side, an example showing The major silicon lines from 250 up to 253 nanometers. And obviously there in the middle we can see the well-known 251 nanometer line for silicon. I did 3 replicate measurements and they're overlaid on each analysis emission line. So starting off with aluminium 167, in my opinion it's not the best line for high intensities. However, it's an excellent line for trace determinations of aluminium. So it's not a line that I'll use for the determination of aluminium in glass. The aluminium 176 is a little bit better, however the sensitivity is lower. Aluminium 308, 309 and 394 are good lines. However, aluminium 396 I think gives poorer precision because of the extreme intense calcium 396, which is just on the right hand side of this line. There's argon, argon 404. Argon emission lines are useful as a diagnostic tool. They indicate if the plasma is stable and if the nebulizer gas flow rate is stable. So you can see almost exactly all 3 on top of each other. Same with argon 420, 430, and then we get to boron. So with some of our first analyte lines, boron 136, probably not an emission line that I'll use. This is just for interest really. Boron 182, 208, 249.67 and 249.77. Barium 230, 233 and 455. Then calcium 184, 315 and 317. Calcium 422. Calcium 393 and 396 were far too sensitive to measure on the ICP. They saturate the detectors. Cobalt 228, 230 and 238. Chromium 205, 267, 283, and then copper 224, 324 and 327. Iron 238, 239, 259 and 373. Potassium 766 and 769. And then the only line for lithium 670. It's the only useful emission line. The other lines are not sensitive at all. Although this is actually a conglomerate of 2 emission lines, and that's the reason why the lithium looks a little bit lopsided. Magnesium 279, 280 and 285. Manganese 257, 259, 260, 294 and 403. Sodium 330, 588 and 589. Then on to nickel 227, 231 and 232. Lead 168 and lead 220. My opinion is that the 168 line will be a little bit better because there's an aluminium emission just on the right hand side of 220. Sulfur 180 nanometers. This line has an overlap from calcium 180, which cannot be resolved, and it's important to do an interference correction after calibration. But sulfur 182 is free from that interference, and that was probably the preferred line. Tin 147, once again just for interest, 175 and tin 189. Strontium 407, 421 and 460. And then titanium 323, 334 and 334.9. 336. Vanadium 292.40 and 292.46, vanadium 311, and then tungsten 207, and this sample gets contaminated with tungsten because it gets milled in a tungsten carbide mill. This emission line simply confirms the fact, and that we can probably use this as a monitor line. Maybe it can indicate the milling time later on as well. Tungsten 239, and then zinc 202, 206, and 213. And lastly, zirconium 339 and 343. Once again, if the sample gets milled in a zirconia mill, you would not be able to determine zirconium. So onto the silicon lines. There were 97 different silicon emission lines. I'm just showing 4 of these silicon lines, but the rest are available if you want to have a look at it. So the well-known silicon 251 nanometers, and you can see that the intensity is quite nice at the 1 billion counts per second. Silicon 390, 167, and then silicon 178. It's not a very sensitive line, but this line can be used for those elements that are at the low concentration range as well. Now getting to precision. So the following tables show the analyte emission line, the corresponding best silicon internal standard line that I used, as well as the precision without the internal standard, precision with the internal standard, and then the improvement factor. So there are a huge amount of data coming up. Probably best to look at it in a spreadsheet later on. So firstly, we start off with aluminium, and you can see that the aluminium 167 line was referenced to silicon 153. Without the internal standard line, the RSD for aluminium was 11.3. However, with the internal standard is 1.53, which is an improvement factor of better than 7. However, if we move over to, for instance, aluminium 394, which was ratio to silicon 298, the RSD before the time was 17.7, but with the internal standard it's 0.3. That is an improvement of 56 times. Once again, as I alluded before, the aluminium 396 doesn't have as good a precision, probably because of the calcium emission that's extremely intense just to the right hand side of it. Furthermore, there's results for boron and barium. Then continuing on to results for calcium, cobalt, chrome, copper, and the beginning of iron. Then iron, potassium, the only line for lithium, magnesium, and manganese. Continuing on to sodium, sodium, nickel, lead, and sulfur, as well as tin, starting with strontium as well. Continuing with strontium, titanium, vanadium, zinc, and lastly zirconium. So the improvement factor for titanium 334.9 was 1420. I think it was just a fluke, but on the next slide we'll see the typical improvement factors. So looking at the improvement overall, the average improvement factor was 68, the median improvement factor was 44.5. Worst improvement factor is 4, and the best improvement factor we just looked at was 1420. If we look at the histogram, let me just get there, 21 results were had an improvement factor from 50 to 100 times. 18 emission lines had improvement factors between 20 and 50. 9 had improvement factors from 10 to 20, and 10 lines had improvement factors from 5 to 10. There were also 8 lines with improvement factors between 100 and 200. Then the one outlier, I would say, as well as some lines with improvement factors under 5. So lastly, on the conclusion, we believe there's excellent improvement in precision using the matrix element as an internal standard. The internal standard lines should be selected based upon a complete calibration and several samples, not just a single sample. However, this time around we only had the one sample to work with. So in future, what we'd like to do is perform a complete calibration based on a silica blank, several CRMs, and we want to generate a complete set of calibration curves. After that, measure several samples, compare the results to XRF results, and also measure some CRMs that were not included in the calibration. So with this, thank you once again. We look forward to doing some more future work. I hope you have a wonderful day.